Today we're covering circle segment cutters. The benefits of using these type of cutters are faster machining times. Typically we can take bigger steps with better cutter engagement. So we're using less time stepping down wall surfaces and floor surfaces. Typically we can also attain better surface finishes when the right speeds, feeds, and chip load is applied. And we can also see longer tool life because we're cutting with more engagement of the tool. In Cimatron, this has a wide range of applications that we can use it in. We can use it in roughing, rough parallel, rough spiral, volume pocket. We can use it in finish horizontal, planar areas, finish mill all, finish by limit angle. We can use it in pencil and rest mill, local operations, and 5X Pro procedures. Most of the time when using these type of cutters, what can be tempting to do is to try and use it for every situation. Traditionally, we put in a bull nose and we just start cutting everything. This type of tooling is specific to the surfacing you are working with. So each tool has an ideal angle range that it works in. So we wouldn't want to load one tool, let's say a barrel cutter, and then try and finish a whole core with it, unless that surfacing was ideal for that type of tool. So usually there are angle ranges that we'll go over later here that are specific to each type of cutter. Most people will see the biggest benefits when you're able to stick in those angle ranges, use these type of tools, and put them into 5X production procedures. When you're able to do that, we're able to tilt the head and stay in the best angle range more of the time than we could traditionally in 3-axis. So 3-axis still has its applications. 5X has slightly more that it can fit in. With Cimatron, there are three types of cutters that we support, three shapes: barrel, lens, and oval tools. The one thing we need to keep in mind when we're trying to define barrel cutters in Cimatron is that we have to be able to define the flat bottom diameter, and we need to define the profile arc. Next, we're going to go over and take a look at the process to actually go through and set up these cutters for the oval, barrel, and lens. So now I'm going to do a top view here, and I've brought in some of this information from the manufacturer's catalog. And what we can see is the shape and where this information comes from. 10 millimeter will be what we stick with for most of the day here. And I'm going to start by just making a new tool and give this a name. We're going to switch the technology to special. We're going to go to oval. The diameter is D1 right here. And it's 10 millimeter down here. So this is okay. Now the tip radius is going to be the small diameter on the end here, which is R1, and R1 here is 2 millimeter. Now the profile radius is going to be the large arc, the side of the tool, which is R2 up here. For this cutter, that is 85. So we're going to punch that in. The cut length is going to be L2. So when we come over here, we can see that's 26. And the clear length is going to be standard for all tools that I make today at 1" 750. I'm going to leave the extension in the holder. Now, one thing you'll notice is when you make these tools, It actually is going to give you some useful information here. Mills best at slope angle range 73.9 to 90. This again goes back to why these cutters are not made to cut everything. They're application and surface specific, and you want to use them in the range of angles that they are best made for. So one thing you'll actually see is we're going to expand on that in the next version and actually let you cut in these ranges with more control. So you have that to look forward to. But for right now, when you're machining and setting this up, you just want to look at this, and it's a nice tool to kind of keep in mind when you're programming and make sure you utilize that as best you can. So that is our oval tool. Now we're going to set up our barrel. Let me zoom out here. Now, we're going to switch this to barrel, and my diameter, D1, is 10. That's okay. My tip radius, right here, oops, one thing to look at here, we have ball and bowl. In this case, this cutter is a bowl, because when we look at it, there is no defined radius on the end here. So we either need this flat distance right here or the radius if it has one. In this case, the catalog does not specify. So what I did is I actually went over and grabbed the step file that they have, pulled the cutter in, and just measured it. And this is flat on the bottom, and it's 4 mm. So what we can do, flat bottom here I know is 4. Corner radius we do have, that's R1. So we're going to come to here, and that's 2. And now the profile arc is going to be the large radius on the side, R2 up here, and that's 50. So we've got our flat bottom, we've got our cut length. The cut length we need to punch in here. That is going to be L2, which is 21. And now that we have that information, we're going to use the standard clear length. And again, you can hit this button, zoom in, and manipulate. Oops, wrong button there. Bounce back, zoom in, check this tool out, make sure that it's what I want. And again, we get a different angle range here. We get 78.3 to 90. So slightly different, but similar to what you see with the oval. I'm going to green check to apply that. And now we have one more tool to set up. The barrel is really the trickiest one, because if this information isn't here, you don't have the end radius or you don't have the flat, you have to get that information. We need one of the two. So in this case, the cutter manufacturer provides that information. It's just not right in here in this quick display. So we just snag that file from the website and do a quick check. So now we'll move on to our lens tool. And this will be lens, and this will be ball. So when I move over and check out our information here, there is no defined flat. There is no flat on this cutter. And without that flat, that makes it a full ball instead of a ball nose. If it did have that, we could define it. But in this case, the one we're using today does not have that. So diameter here, we're going to go with D1 again, just 10. We already have that. Tip radius is going to be the large arc, which is R2. So when we come down, that's a 20. Our corner radius is going to be our 1, which is 1. Okay, now that we have this, we can see we've got a nice dish. We have seen some customers use this to represent a high feed mill. So they're using this to better represent the stock when they use that type of cutter. It tends to update and get a better representation. So not necessary, but for those of you that have wanted a better representation of a high feed cutter, this is one way you can do that and get accurate stock left behind. So just an option, just so you guys know it's there. Now that we have these cutters, we're going to green check. Oh, you can see again here, the slope angle is dramatically different. This is 0 to 12.2. This is all just really good information to kind of keep stored when you're trying to cut and use these best. Now, we're going to go up here to oval. Let me turn all this other stuff off. We'll get rid of barrel, get rid of lens. Let's see what we're working with here. Now I've roughed this out and I've finished this down with a bull nose. And as we could expect, this is 3-axis. What we're going to have here is going to be a lot of cusp left behind with the stock when this steps down. So this material is going to be jagged here. Now, when we use a ball, we get slightly better engagement when we come down, but it's still going to be leaving behind at that step some stairs for us to sit there and finish. So the only way to get rid of that is to decrease the down step, which is going to increase the machining time. And the big advantage with these other tools is reduce machining time in the right application. So we're going to copy this down. We're going to edit the procedure. And the only thing we're going to change here is the tool. Here we're going to grab our lens tool. Oh, I'm sorry, oval. Oval. There we go. And we're going to save and, oh, let's actually cut the other side here so we can kind of see the difference between the two. Calculate this. Now the toolpath will look very similar from side to side. You can see we have a different start, but they're very similar when we look at them. So that is to show with the same step what we're going to get with that. Now, when we place this tool and we look at this from the side, look at the cutter engagement difference. So even in 3-axis, in the right application, we can see a dramatic increase in the surface contact of that tool when it's used correctly. Now, in 5-axis, we can do more tilting to keep it better engaged, and that can make an even bigger difference, and it's what most applications it's going to get used for. But you can see here in this 3-axis application, you're cutting down a tall standing rib, something like that. This can do a lot better job finishing down quickly versus traditional tooling. So you'll see an increase in the surface finish as well, typically. So now when we look at the stock left behind here, this is what we're dealing with on the wall with the new cutter, and this is what we get with the downstep on the other side. You can see we have these standing material is just not as good. So we're going to have less machining time with that oval tool in this scenario. Now let's move on to the barrel cutter here. We'll get this turned off. Now, we've roughed this out. We've cut this down. And when we put this 10 millimeter ball on here, we're getting engagement on the wall that is what we typically do, but to avoid the stair stepping, we'd have to reduce this to get a very small step going down the wall to get a better finish. Now, in this case, we can see this is leaving behind. It's not too much, but still, we would have to reduce that down step to get a better finish. Now, if we copy this, we're going to try a barrel cutter here. So we'll come down, turn that off, switch to a barrel, tells us the ranges it wants. I'm going to unpick this side so we can see it, and then pick this side. Now, it should look similar here, but the big difference is going to be the cutter engagement again. When we take a look at the side here, we can see our steps are similar, but the cutter engagement is much greater when it comes down this wall. So we're going to see an increase in the surface finish quality. We can see over here, we have a very nice cleanup coming down the wall. And then when we come onto this side, we've still got our steps that we're dealing with. So our traditional ball tool would need much shorter down steps to try and match what we're going to get out of that barrel cutter. So reduce machining time, increase surface finish quality. Now for the 5-axis people, we want to show this because it's going to make most likely the biggest impact for the people who have 5-axis. When we look at this lens setup here, we've got a rough that's knocked this down. And again, we could have used the lens tool here. It would give us an accurate representation if we were using a high feed cutter. So what we can do, and traditionally this is what we would do, is go ahead and get a nice path on here and mill this up. So we tell this to go through and cut this all up. But what we're left with, if we have too big a stock step or step over, is these cusp heights left behind. Now, if we take this same path, same diameter cutter, but we switch it to a lens tool, we're going to change this guy out from 10 millimeter ball. We're going to use a 10 millimeter lens. We're in our angle range. And then I'll switch the drive over to here. We'll switch the curve over to here. Let this stock catch up here. Now, looking at this, you don't see a huge difference. They're both pretty good paths. Where we're going to see the difference is when we throw these in the simulator. So let's kick this over and actually run these guys through. So we're going to run this a little quick just to get through this so we don't take up too much of you guys' time here. But when I let this go through, so this is the lens side on the left here. What we're going to use here to analyze this, they look fairly similar. When we look at these, they look fairly similar. It's not obvious that there's a difference. So what we can do is use this stock analysis tool. And you guys probably saw this in the last simulation webinar, but we'll go deviation distance from part here. And it analyzes the distance between the part and the remaining stock after simulation. and it bases these colors on the distance between the part and the stock. So I'm going to hit go, and here's what it tells me. This green right here on the left with the lens tool, we're looking at light green, so we are plus or minus 4/10, which is the tolerance for my procedure on all of these. That's telling me it's right there. It looks really good. Now, this side, not so much. What this is saying is we got to go up. Now we're talking this light blue on the edge, we're looking at between 7/10 and 1,000 2/10. We get into the dark blues here, we're talking up to 1,500 and more that is left behind. So we clearly could not run and get comparable results between the lens tool and a ball of similar diameter. We'd have to use a much smaller side step to get the same surface quality with the ball. So these tools in the right applications, used in the right range, can give us significantly reduced machining times and better surface finishes. So just trying to show you guys some of the options you have available, some of the tools that you have, and how to set them up inside of the software. And yeah, if you guys have any questions, let's see.